Hey everyone, long time no see. Sorry for the delay in getting this one posted. Getting back from Italy kind of took a little bit longer to get everything put together than I'd planned on. So without delay, here is a lecture on rocket propellant toxicology. So in this we're going to talk about the various propellants that get used in the different types of rockets. So oxidizers and fuels and things like that, and then the toxic aspects of them. First, before we get into that though, we'll start off with just some basic terminology type of stuff, because I may use some terms that aren't necessarily as commonplace and just routine everyday language if you're not a complete space nerd anyway. So this will get us all on the same page. So first up, a bipropellant. So a bipropellant, it's a fuel that has two different components, so a fuel plus an oxidizer. So in general, when if you guys watch that How Do Rocket Engines Work recording from Everyday Astronaut, so remember from there that fuel and oxidizer mixes together. If they're hypergolic, which is going to be one of our terms, meaning it spontaneously ignites, then that's enough to create the thrust. If they're non-hypergolic with each other, so they have to mix, they get fed a spark and then they burn together. So a bipropellant has two components, the fuel plus the oxidizer. Cryogenic basically just refers to liquefied gases that they have to be kept refrigerated to stay in the liquid state, at least under atmospheric pressure. No amount of pressure will liquefy gases that are above their critical temperature, which sometimes they use arbitrarily as a minus 240 degree Fahrenheit as the upper limit of the critical temperature. So if you ever watch a SpaceX launch the Falcon 9 rockets, they use liquid oxygen as their oxidizer, which is a cryogenic fuel. So that's why you see all the clouds of smoke, the clouds of oxygen coming off of it, because it just can't be kept liquid under atmospheric pressure, so it has to stay super cold. Specific impulse, or ISP, you'll hear this used a lot in rocket terminology. Basically, it just describes how efficiently a reaction mass engine, so a rocket engine, creates thrust. Overall, you're looking at it in terms of the unit of measurement is in time, typically over seconds. So if a fuel combination has an ISP of 240 seconds, it basically means it's going to burn for 240 seconds. So it'll give you that intrinsic amount of thrust. Delta V, so typically is thought of as a change in velocity. When you're talking about rockets, a little bit different though. It's technically called the measure of impulse per second of a spacecraft mass needed to perform a maneuver. So nice, simple, straightforward definition there. Simpler way to think about it is it's the change in velocity that a spacecraft can achieve by burning its entire propellant load. So start off from 0 miles per hour, 0 meters per second, length per time, and then what's your change in velocity after you burn your entire prop load. So that's going to be your overall delta V, and you use different velocities to calculate how much fuel you actually need on board to hit that. So whether you're looking at an escape velocity to get out of the gravitational pull of the Earth, you're looking for orbital velocity to maintain an orbit around the Earth, like the space station. That's your overall delta V, and then you have your fuel calculations that are based on that. Hypergolic, already mentioned, means it's self-igniting. So when you put these two fuels, you put a propellant and an oxidizer together, as soon as they touch, or at least within 75 milliseconds, it's a major explosion. So hypergolic fuels are awesome for rocket engines. As long as they're reliable and they burn effectively within 75 milliseconds. And we'll talk a little bit about why that could be an issue if they don't. Monopropellant, it's a single substance, and it can either be a single compound or it can be a mixture of propellants or fuels and oxidizers that are put together into one fuel, which are stable under normal conditions. And that stable under normal conditions is kind of the kicker with that. They'll either combust or decompose and then create the hot gases needed to propel the rocket once they're ignited or catalyzed. There are some monopropellants that are in use. Most of it, though, is two separate There are bipropellant that are used in rockets. And the propellant, just as an overall term, fuels, oxidizers, monopropellants used to provide energy in the working fluid for thrust of a rocket engine. We'll talk about working fluid in a little bit. There we go. When you're looking at time periods for storage, you're typically looking at 5 to 10 years on average, but ideally you're looking for over 20 years if you're going to use it in a satellite. 5 to 10 years. So when we're talking about, let me kind of back up for a second. When we're talking about these propellants, we're talking mostly about use in space. So for rockets, space vehicles, things like that. This also pertains, though, to things on Earth, so like missiles, some military applications too. Sometimes on jets, which we don't really have them anymore, we've actually run out of them, but something called JATO, which is a JATO rocket, which is a jet-assisted takeoff. So these little rockets that would get strapped to the side of airplanes to help facilitate taking off a lot quicker. Sometimes they'd be used in the air to get a little bit of go juice to pick up speed pretty quickly. Actually, we've run out of JATO bottles, which is a completely different story, but for that, I mean, you're looking for about 5 to 10 year storage period before they'd start to decompose, because in theory we're going to use most of those within that time frame. For satellites, they're going to be up there for a longer amount of time, so you want something that's going to be pretty stable for a longer period, so we're looking at about 20 years. And the low freezing point is generally required, so something that can withstand colder temperatures before they freeze, because if your liquid propellant freezes, you can't use it. So you want something that's stable to a lower freezing point. Okay, now the overall term rocket propellants, I've already mentioned it, but this encompasses fuels and oxidizers that we use in the biopropellant systems, and then also single fluid monopropellants. So when you hear someone talk about a rocket propellant, intrinsically it means your oxidizer plus your fuel put together, and that's what propels the rocket forward. These can be classified as either liquid propellants, which is what this lecture is going to focus on, is the liquid propellants. Solid propellants are also in there, which talked about that pre-grained, or no, actually we didn't talk about that, but solid propellant is something that, so like the side boosters on the space shuttle, so the smaller pointy ones on the outside, those were solid propellants. Basically what they do is they take their fuels and oxidizers, put them together into a solid, so you can think about it, it's like how black powder works. So black powder, or gunpowder, it's a solid propellant. So it propels the bullet out of the chamber, or out of the barrel. The only problem with solid propellants is that they're not throttleable, which means that for the space shuttle side boosters, or once the space shuttle launches, or also for SLS, the Space Launch System, so the new big rocket from NASA, once it launches, it uses solid propellant side boosters. Once you start those, you can't turn them off. They're going to burn their way all the way through. There are a few tricks that you can do to make it where it's kind of a pseudo throttleability. So, for example, when a rocket launches, it goes through a phase called max Q, which is the point of maximum dynamic pressure on the rocket. So when they go through that, so all the forces that are working on the outside of the rocket, they're at their max point. They end up throttling down through that, so it decreases the overall pressure, keeps the rocket intact as it makes it through there, and then it can throttle back up. So what they can do on the solid propellant side is they can build this in different layers where, they have their launch layer, which is full power, and then once they, that would be a timed burn, and then once they get to the point where they'd be going through max Q, then they can have a different fuel to oxidizer ratio in there, or decrease the grain production in there, and which would decrease the overall thrust. And then once they'd make it through that, they'd have that timed out, and then they'd hit the next layer, which would go back up to what would be considered full thrust. So there's some ways to make it kind of pseudo throttleable, but in general, once you light the candle, then it's going to go until it burns out. And then finally you have hybrid propellants, which includes one liquid component, which is usually the oxidizer, and then one solid green component, which is usually the fuel. You can reverse that, but most of the time it's a liquid oxidizer and then a solid fuel. We're only going to talk about liquid propellants. I mean, you could honestly make up an entire course just based purely on rocket propellants and everything that goes into them. It's actually a really, really interesting topic. If you're ever completely bored and looking for something good to read, there's a book called Ignition by John Clark. He was one of the guys that He was around in the 40s and 50s and 60s and did a lot of the pioneering research on rocket propellants. May make it sound like a boring book, but it's actually really, really interesting. I actually read the entire book on the plane on the way to Italy. So it's an interesting read. Again, something, if you're interested in this kind of stuff, I would definitely recommend that. Okay, so we're going to talk about some ideal characteristics for a rocket propellant. So we want something that's high performance, but it doesn't weigh a lot, which makes sense. You know, you want maximum thrust, but you don't want so much of the weight of the vehicle be tied up in that fuel weight necessarily. And then the physical and chemical characteristics have to meet the operational environment requirements. So, for example, if you're operating a missile system, and this missile system is deployed in Alaska or somewhere where it's going to be pretty cold, you don't want to use propellants that have a higher freezing point. So if your propellant's going to freeze at 30 degrees, it's probably not a good idea to have an environment where the average temperature is going to be, you know, close to zero or in the negatives, because your missile system is not going to work then. Same thing if you have a boiling point that's at about, you know, 90 to 100 degrees, you probably don't want that propellant to be in the tropics because it's going to all boil off. So you have to find the right, so it's not necessarily picking the most powerful fuel oxidizer combination and putting it together and then using it for everything. If that was the case, it would be a really easy thing, but you have to take all these other mission parameters and take them into account. So overall your environment is kind of a big thing. Also, you know, when you're looking at terrestrial use in missiles, you don't want to use something that's cryogenic. I mean, because when they're using these surface-to-air missiles, they're not fueling them before they're launched. I mean, if you have an enemy jet that's coming into your airspace, getting ready to blow you up, and you need to blow them up first, you don't have time to go out and fuel the rocket. You have to have these, you know, storable fuels that are already loaded and ready to go. So using a cryogenic in that type of setting, it's not going to be feasible. So you would need something that's storable with a wide range of temperature efficacy. Anyway, so that's something to take into mind when developing fuels. The next thing is chemical energy. Your overall propulsive force comes from the hot gases that are being ejected from the rocket engines. And this looks like it's a Falcon 9. It looks like the engine's on the bottom of a Falcon 9 right there. But the hotter the gas, the more propulsion you're going to have that goes along with it. So getting your maximum flame temperatures and your maximum gas per unit weight is key. So the more that you can move out this back end, the hotter it gets, the more you can move, the more propulsion you're going to have, the better your delta V is going to be. And it's ideal to have a low molecular weight of exit gases. So you want that mass flow, the flow of that mass to be moving as quickly as possible, and something that has a lower mass total is easier to move faster. So you want a maximum mass flow rate, which means you need a minimum mass to maximize the velocity of that. Liquid range, so I already kind of blew it, talked about that a little bit earlier, so I won't belabor that, but you know, your operational environment has to be taken into account. Missiles have to have a wide operational range. Stability, so they have to, yeah, so I've already talked about all this basically. So storage is going to be a key there. Also, density is a very key thing. So you want your ideal propellant is going to be something, one of the characteristics, it has to be high density. So the higher density that something is, you have a greater ability to shove more into a smaller tank. So over here, if you look, this is the Starship, and I'm not sure which serial number or version that would be, but anyway, it doesn't matter. So how a Starship is set up, so you have the cargo space up here, but then these are your fuel tanks. So right here, this is your methane tank, and then this is the liquid oxygen tank right down here. So liquid oxygen in this case is the oxidizer, the methane is your fuel. Those get piped down, they get mixed into the combustion chamber, and then you get your propulsion that comes through there. So this combination, it has a better density, so you can pack a lot more into a smaller space. You want to minimize the overall inert weight of the rocket. So the lighter that you can make the rocket, the better off you're going to be. There's a huge weight penalty that goes along. So for every pound that you carry into space, it carries a huge penalty in terms of energy requirements. So if you can make the rocket overall lighter and pack more fuel into it, then you're a lot better off. So that's going to be the key. Also, you want viscosity is a goal. So low viscosity fluids, they have less of a pressure drop throughout the entire feed system. So you don't want something that's high viscosity, because you're going to have different pressures in different areas of the feed system, and that can really jack with the ability to get it all into the thrust chamber or the combustion chamber, and it'll mess with your thrust. And then also, if you have something that's lower viscosity, you can use smaller fuel pumps or a lighter weight pressurization system. And that goes back into the fact that there's a huge weight penalty that goes in to carry things into space. So the lighter that you can make it, the better off you're going to be. And so by using lower viscosity fluids, it helps you minimize the weight that goes into the fuel pump or the feed systems. You want something that ignites very reliably. The hypergolic fuels, so the fuel plus oxidizer that automatically burn when they come in contact with each other, that's absolutely ideal if you can get it. They're the most reliable. It doesn't require a secondary ignition source. So if you're using something that's not hypergolic, they'll mix with each other, but they won't blow right away. So which means that if you're using non-hypergolics, so let's say that you're in space, so this is a second stage of a Falcon 9. So this is entering into orbit, it's trying to get to its right place, to the right orbital altitude. Sometimes it requires multiple burns in order to do that. So, your rocket takes off, you get the first stage falls away, second stage continues. Sometimes they'll have to go into a transfer orbit, which I won't get into different orbital characteristics, but sometimes they start off in an orbit, then they have to transfer to another orbit. So to do that requires multiple burns. So what you want is something, when it comes time for that second burn, you want something that's very reliable, that's, that you know is going to work. If you use non-hypergolic fluids, it's going to require a separate igniter. And those aren't always super reliable. And you're going to have different pumps, and maybe you have these different we call it starting slugs or hypergol slugs that will get the process going. You basically just need a separate ignition system to get that all going. So the easiest way is to just avoid all that and use hypergols. So use hypergolic fluids that is going to explode right away, so you get that second burn capability. You get multi-burn capabilities to go along with that. All right, now a few basic principles of rocket performance and how all this starts coming together. So reaction engines or rocket engines, these are all governed by Newton's laws. So one quote that goes along with it: all ship propellers, airplane propellers, oars, everything else, they generate their forward push at the expense of the momentum of water or air masses that are accelerated towards the rear. So this uses the working fluid, and these working fluids can include cold gas, the decomposition products of monopropellants, the combustion products of biopropellants, or molecules that get heated by electrical, solar, or nuclear energy sources. So in other words, taken a different way, by accelerating a working fluid, so whether that's air, water, combustion products, whatever else, by accelerating that out the rear of a vehicle, that's what generates your forward thrust. So the thrust of a rocket comes from the high velocity of the exhaust products that exit the engine. And so for this, the easiest way to think about it is a balloon. So if you blow up a balloon, the energy source is the elastic energy, that stretched rubber of the balloon. The working fluid is the air that's inside of the balloon. I should have just went and got a balloon and blown it up, but you can imagine. So the working fluid is the air that's inside the balloon. And then the exhaust nozzle is the, I don't know why I'm doing this, but the exhaust nozzle is the hole at the other end, or wherever the air is going to come out of. So when you unpinch or let the balloon go, so at the exit plane of that balloon, so right at that exhaust nozzle, the air is flowing a lot faster than the air that's still inside of the balloon. So it creates this pressure differential. you get different velocities. You get a higher mass flow rate, which propels that balloon in the other direction. So, how a balloon, when you blow it up and let it go, that's the same basic principle as how a rocket flies, how a boat moves through water, how an airplane can be propelled through the air, not necessarily how it stays up in the air, but how it gets propelled through the air. All right, just a couple of equations. It's helpful to kind of know what these things look like and what they'll govern. So rocket performance is governed by Newton's second law, which simply says that the rate of change of momentum is proportional to the net external force that acts upon the body. So this is described by the equation force equals mve plus pe minus pa times ae, where m is your mass flow rate of the working fluid. And so that's measured in pounds per second or kilos per second, basically a weight per second. So how much weight of that working fluid or that propellant is moving through over a given period of time. VE is the exit velocity, so the velocity of the working fluid where it exits from the free body. So that's in basically distance per time, so feet per second, meters per second, whatever. PE is the exit pressure, so it's the pressure of the working fluid at the place where it exits the free body. So what's that pressure at where it exits from the body? So what's the pressure of the air leaving the balloon? And that's measured in pound per feet squared or pascals. PA is the pressure in the surrounding of the free body, so the area of pressure, and that's same units, pound per feet, pascals, pound per feet squared. And then finally, AE is the area of the exit of the nozzle. So how big, what's the diameter of the nozzle that you're working with? And that's in feet squared or meters squared. MVE, so this segment right here, this is also called the velocity thrust. And when you look at calculating rocket performance, this accounts for 90 up to 100% of the total thrust of a rocket engine. PE minus PA times AE, this is called the pressure thrust, and it accounts for very, very little of the overall thrust. So it's about 0 to 10%. So basically when you look, so the higher the flow rate, the higher the thrust of the rocket's going to be. And also the higher the exit velocity, so the faster it's coming out, the greater your thrust is going to be. So for a fixed flow rate of working fluid, this equation shows why rocket engineers really try to maximize that thrust per unit flow rate by maximizing the exit velocity. So the better that you can get your exit velocity, the more thrust you're going to have available. All right, one more equation. This is considered to be the rocket equation, so this is kind of a big one. You guys aren't going to have to calculate anything with this, but it's definitely good to know what this is. So the equation is your delta V is equal to VE times the natural log of MO over MF is equal to your specific impulse times G sub 0 times the natural log of MO over MF. Okay, it's a lot of stuff, so we'll work through it. So your delta V, so that's, remember, the change in velocity that you'll see after burning your entire propellant load, is equal to your VE. So VE is equal to, VE is equal to your specific impulse times G sub 0, and this is the effective exhaust velocity, where in this, your ISP, your specific impulse, is measured in dimension of time. G sub 0 is your standard gravity, so 9.8 meters per second squared. M sub 0 is your wet mass, so your fuel plus your vehicle weight. So you got your rocket loaded, got all the fuel in there, that's how much the whole rocket weighs. MF is dry weight, or M sub F is dry weight, so this is the weight of the vehicle minus fuel. So when you take all this together, if you're given the exhaust velocity, and this is a calculation that is available in some references. So given the exhaust velocity, your desired delta V, so what delta V do you need to get to the place where you need to be? So are we talking about orbital velocity, exit velocity, what are we looking at? And then given the dry mass, so how much does the rocket weigh without fuel on it? You can plug all those components in, and you can solve it to calculate the required propellant mass that you need to get from point A to point B. So it's a long way through it, but just a good equation to recognize where you'd see this and say, oh, this is Tsiolkovsky's rocket equation. All right, so now we're going to switch gears. We're going to talk about oxidizers first, and then we'll finish up liquid oxidizers, and then we'll talk about liquid fuels. So first up, oxidizers. Just general statements about oxidizers. The best oxidizers are made from oxygen and fluorine. You get the best performance from these. They're ideal in terms of performance characteristics. The only problem is that when you're looking at the molecular forms of oxygen and fluorine, so O2 and F2, they're cryogenic, which means that you're kind of limited in use. Cryogenics are hard to work with, require a lot of specialized equipment to get them into the rocket, to keep them in the rocket. They're obviously super cold, so they don't work well for all indications, but they do provide the highest performance from an oxidizer standpoint. Chlorine and bromine actually have better physical properties overall, but the problem with these is the molecular weight is too high and it can degrade performance overall. So there are some oxidizers that use chlorine or bromine that have them as components of it. Some of the exotics have bromides, or boranes, I'm sorry, like pentaborane, but molecular weight's too high when we're talking about chlorine and bromine, and it can degrade performance overall. Nitrogen is also included in a lot of oxidizers. It doesn't really add a lot to performance, but it's used as it's a great backbone to kind of build and add on your oxygen and your fluorine, so you can build up these good robust molecules using nitrogen as your backbone. Now hydrogen's actually a fuel that gets used, but it's a great working fluid. It's the first element on the periodic table. It's the lowest molecular weight, so it's really light. And it gets incorporated in some oxidizers because it is such a great working fluid. But anyway, the majority of oxidizers, the best performance you're going to see comes from oxygen and fluorine. So first up, we're going to talk about cryogenic oxidizers. So if you look here, this is a picture this is actually the Demo 1. So Bob and Doug, the two astronauts that went up basically on the maiden voyage of the manned SpaceX Dragon capsule. The Falcon 9 rocket uses liquid oxygen as its oxidizer. We'll talk about RP1 or rocket propellant 1. It uses as its main fuel, but it uses liquid oxygen as its oxidizer. So whenever you watch a Falcon 9 launch, you'll see all these clouds that are coming off of it. People have thought like, oh, it's on fire. But that's totally normal. Liquid oxygen, it's a cryogenic, so it has a very think about it as a low boil off or a low boiling temperature. So it boils off very easily. So it's hard to keep it in the tanks. You have to have this continuous resupply going. And in this continuous resupply, it generates all these huge clouds that come off of it. So whenever you see something creating major clouds like this, it's a cryogenic that's going into it. The first cryogen that we'll talk about is ozone. So ozone, it's an allotropic form of oxygen. It's a colorless gas, but if it gets cold enough, it's actually a really cool looking deep blue colored liquid. If it gets too cold, it becomes a solid, but that's a different story. It's been studied as a potential oxidizer since the 40s. It's got a lot of promise that comes with it, but it's really not widely used today. They make it commercially using something called the Welshbach process, which you don't have to know about, but involves an electrical glow discharge into a stream of oxygen, and then you get this O3 with a 116 degree bend and the three molecules of oxygen that get put together. What makes it attractive overall as an oxidizer is that its liquid density is a lot higher than oxygen. So remember, you want to maximize density so you can shove as much into the tanks as you can. And then also, when a mole of ozone decomposes, or when it decomposes to oxygen, it gives off around, I think it's like 34 kilocalories of heat, which is awesome because that boosts overall energy performance, because the hotter you get something, the more propulsive force you're going to have. So it's got those two things going, the density and then the thermogenesis of it. The problem is it's just as toxic as fluorine is, which we'll talk about on the next slide. You can stabilize it with fluorine, but it's really not enough to be useful on a wide range of applications. But the biggest reason it's not a super good oxidizer is that it's murderously unstable. I mean, seriously, if you look at it wrong, if you give it kind of the side eye, it'll explode with more vigorously than you can imagine. So it's very explosive, it's very unstable. It can be stabilized with fluorine, but not enough to make people feel comfortable working closely around it. I mean, I personally wouldn't feel comfortable if I had the chance to go into space and ozone was being used as the oxidizer. It's probably not a great thing. I really don't want to sit on a huge explosion. The other issue is from a toxicologic standpoint, it can cause fatal pulmonary edema pretty quickly. So if you inhale enough of it, it'll really start to cause edema in the lungs. It doesn't cause severe upper respiratory injury, which is kind of odd, but it can cause life-threatening pulmonary edema. So again, it doesn't have a lot going for it. Again, it's got good density, it's thermogenic, but everything else kind of works against it. I mentioned fluorine. So fluorine's been one of those that's been evaluated extensively since probably the 40s and 50s, more so in the 50s. It's seen some successful use as an oxidizer, but it hasn't really been used in an operational program yet. It's very toxic is a big problem that goes along with that. It's one good thing is that it's very reactive. It reacts with almost anything, except for nitrogen, some of the lighter gases, things like that. But it's very reactive, very hypergolic. Problem with that, though, too, is that if you're going to have a tank, you have a container holding fluorine, you have to make sure that thing is clean beyond clean beyond clean. It has to be extensively cleaned and extensively passivated. So passivation, I should have this in terminology, but it's a process that you can use to make metal and plastic surfaces non-reactive with a propellant. So in this case with fluorine. Usually involves you clean it extensively beforehand, so you clean every single nook and cranny, and then you gradually start introducing the element into the piping and tubes in the tank itself. So it's kind of like a desensitization protocol with penicillin or something. So you use a very small amount, and then you gradually increase it, kind of get the system used to it. But you have to do this very carefully. If there's any grease, any fluid, any impurities, anything at all that's not supposed to be there, fluorine will react violently with it. There are stories, I think, from Bell Aeronautics. They made the X-1. Some other aircraft, they were working on using fluorine as an oxidizer. So like the X-15 was North American, but used rockets, and so it had fuel plus oxidizer. But all these companies were doing testing on fluorine to see how well it would work. And there's a story of where fluorine kind of ate through one of the gaskets in the tank, and then it reacted with the aluminum that was in there, and it created a massive, massive explosion. I think if I remember the story right, it was like it ignited the tank, and so it was moving in through the combustion chamber. It started a fire out here, so it looked like you had another rocket nozzle moving up through the top of the tank. You had the fire coming out of the nozzle itself. The engine actually exploded, destroyed everything on the first floor of this lab that they were working in. Very, very nasty stuff. It's also a severe irritant to everything it touches, and it can cause really severe liver injury. Another thing is you can't let it come into contact with water, or else it's going to combine to form hydrofluoric acid, and then even the shortest exposure to that can cause second and third degree burns. So it's very severe irritant. Skin, eye, respiratory tract, liver injury, severe burns. It has a lot of stuff. It's very reactive. It's got a lot of energy that's built up in those molecules. But with great energy comes, the potential for great disaster. They did create something called FLOX, which was fluorine plus liquid oxygen. And it was basically what they did was they started attaching some fluorine to oxygen to try to enhance oxygen performance overall. So Flox 30, which is 30% fluorine, 70% oxygen, it behaves almost just like oxygen, but it gives you about a 5 to 10% performance gain. But again, still you have the fluorine to contend with there. Now, liquid oxygen itself, sometimes I may refer to it as just LOX, so it's the other name for it. A lot of most aircraft that are in use in the Air Force today, or the military in general, use LOX. So they, well, actually, they used to, I'm sorry, I'm going to back that up. They used to use LOX, so they had these liquid oxygen containers on board, and so the pilots to be able to breathe that liquid oxygen. Now they use something called OBOGs, which is an onboard oxygen generating system. So anyway, that's kind of a sidebar. I won't get into that. LOX was first pioneered by Robert Goddard in 1926. And so you remember Robert Goddard and his Orchard with the very first rocket that got launched, which was very cool. Had a lot of great success with it. Since then, it's become the workhorse oxidizer. So probably the vast majority of rocket systems today use liquid oxygen as its oxidizer. The Germans also used it. They called it A-Stoff. I honestly don't know what the Stoff means in that, but it was called A-Stoff. It was the German term for it. They used it in the V2 missile, so the big missiles that Wernher von Braun had the unfortunate hand in developing. Remember, he was developing the A4 rocket, which is going to be used for space exploration, but then the Nazis kind of took over his research and converted it into a weapon, so it became the V2. So the V2 rocket used this A-Stoff, which was liquid oxygen. It's a heavy, odorless, slightly blue liquid, so kind of like ozone, but lighter blue than that. It has a boiling point of negative 297 degrees Fahrenheit, so it's above, or I guess below, that arbitrary minus 240 degree point that makes it cryogenic. So this is definitely a cryogenic substance. And it's highly explosive if it comes in contact with easily oxidizable materials, so you have to be very careful around that. If you combine LOX with organic materials, it's very explosive. The good news, though, is that it's very shock sensitive. So, if you have a container of LOX and you drop it for whatever reason, it's not something like ozone where you look at it side-eyed and it's going to explode. So it's a lot more shock sensitive, which is good when we're talking about rocket propellants. You want something as stable as possible, something that's not very finicky. It's not well suited for missile systems, so being cryogenic, it just doesn't work to load it up on site where you're going to launch a missile. It's oxygen, so it's really non-toxic, non-irritating. There's two big hazards that come along with liquid oxygen. Number one is it's cryogenic, which means that it's unbelievably cold. So boiling point of minus 298 degrees. So you have to keep it below that temperature to keep it liquid, which means if you come in contact with it, you're going to have frostbite pretty immediately. You'll have a severe cold temperature burn. And the other issue is that, fires, they feast on oxygen. So if you have these highly concentrated oxygen pockets, it honestly takes very little stimulus. So if you have all this super concentrated oxygen out in the open, it can start to spontaneously burn. So if you're working with liquid oxygen, I recommend not wearing cotton or wool. Otherwise, if you get exposed to this, you can take a small stimulus and boom, you're up in flames. All right, next up is oxygen difluoride, or OF2. This is primarily being evaluated for use as a space storable. It's below that cryogenic threshold, so it's got a boiling point of minus 228 degrees Fahrenheit, which is 70 degrees higher than LOX is. So you have a little bit more ability to work with it. I mean, it's still... So minus 240 degrees is kind of the arbitrary cryogenic break point, but this is still cryogenic. So, I mean, you're not going to have it in an atmosphere of you have to keep it cold. It's going to boil off pretty easily. It's got about 2% less performance versus fluorine has. So if you're using hydrogen as your fuel, It has basically equivalent performance as fluorine does when you mix those two together. It's also a violent oxidizer, just like fluorine. Remember, fluorine reacts with everything except nitrogen. So oxygen difluoride has the same basic principles here. You have to meticulously clean and passivate everything that it comes into contact with. The good news is that it doesn't attack the valves, gaskets, other stuff in the tankage as violently or as aggressively as just base fluorine does. So you have still not much room to work with there. It's still extraordinarily dangerous. It's just not as aggressive as straight up fluorine is. If you come in contact with it and you're exposed to greater than 0.5 parts per million, just like with fluorine is, very dangerous. It can cause significant pulmonary edema. This can also cause hemorrhage. And then workers that are working around it, even in exposures in the parts per billion range, so we're talking about minute amounts, it can still trigger pretty severe headaches. So it's not non-toxic at all. It's pretty toxic. It's harder to work with, but it does have an advantage over fluorine. It's not as aggressive when it attacks stuff. And then when you're using it in space, it becomes a little bit less of an issue. So you're not you load it the one time, but then it's up there and it's ready for use. You don't have to mess with it after that. Because it's got a lower freezing point, or I guess higher freezing point, minus 228 versus minus 298. As long as you have appropriate environmental controls in place in the spacecraft, you can keep it in a liquid state without any boil off happening, without any pressure buildup. You definitely don't want pressure buildup, because you have to have a way to release that pressure. So if you have pressure buildup and you don't release the pressure, then you're going to explode. So this doesn't. You'll be able to avoid pressure buildup in space, and there's really no need for refrigeration as long space is cold in and of itself. So you keep that environmental control in place, and it'll be an easier time. Okay, next up, we're going to talk about storable oxidizers. So these are not cryogenic. Cryogenics are not storable. They have to be loaded at the time they're used and up until the moment that they're used. Storable oxidizers, on the other hand, these can be kept in containers for years and years and years. These are more optimized for use in Earth-based systems, missiles, things like that. First up is tetrafluorohydrazine, also known as dinitrogen tetrafluoride, or N2F4. This one in and of itself is it's more of a space storable than an Earth storable, and that's all because of the fact that of the pressure that's involved with this. So it can be kept at a liquid under its own pressure, but the pressure required to do that's 400 psi, which is pretty high. So you can keep it under a lower pressure and keep it liquid in space a lot easier than on Earth. So it's not as much of an Earth storable. It's an intermediate to a large family of nitrogen fluorine compounds. It does have some good properties with it. We're not going to spend really any time on this one, primarily because it's super shock sensitive. So we're thinking like ozone level shock sensitive, and it's prone to a spontaneous or violent decomposition. In other words, a big boom. Really, its niche is that it's more of an intermediate for the synthesis of solid oxidizers. And the other problem is it's not reliably hypergolic. And that's one of the ideal properties we want, is something that's reliably hypergolic. I don't think I mentioned a bit. When we're talking about something that has to be reliably hypergolic, that has to burn within 75 milliseconds of hitting it, the issue that you run into is, if you have a hypergolic oxidizer and a fuel, and you run them in together, so you run them into the combustion chamber, they mix. If they don't burn immediately, then they're going to pool up at the bottom, and then more is going to come out on top of it, and then all of a sudden they go, and it creates a massive explosion. So you need that reliable hypergolicity within 75 milliseconds. So basically, as soon as they touch, they have to go. So you need that reliable hypergolicity. Otherwise, it's going to explode. It's either going to blow everything up, or it's at least going to blow the engine up, which isn't good either. So that's what we're talking about when we need something that's reliably hypergolic. Okay, interhalogens. So these are also storable oxidizers. It's just a different group of oxidizers. These are the highest energy earth storables, but they're also very toxic and highly reactive. So first up is chlorine pentafluoride, or ClF5. They first developed it in 1962. They fired it in 1964. It's got great density, so you can shove a ton of it into a small tank, and it's the best of all of them. It's the best performing storable oxidizer, but it's a pretty unforgiving oxidizer too. Overall, I mean, it's a good storable, but the military's been pretty reluctant to use it because it's super reactive. If there is an inadvertent release of it, it poses a major toxicologic and tox hazard and a fire hazard too. It's been used in a lot of different rocket engines and subsystems. It's got great performance, great density. Again, so shoving more into a small tank. It's cool. It's been demonstrated to be stable for over 20 years in a small tank, so that makes it good and should be good in missiles and satellites and things like that. But again, it's very reactive. It's very toxic if it gets out. It reacts with water to form hydrofluoric acid and chlorine gas, which hydrofluoric acid we know burns. So that's not a good thing. If you touch it, it's going to burn, especially if it absorbs any water, or if it's hygroscopic. Hygroscopic meaning it absorbs the water out of the air. And then the development of chlorine gas. I mean, chlorine gas is a chemical warfare agent. Kills a lot of people. There was I can't remember if it was in this course or not, but anyway, in the Middle East this last year, there was a chlorine gas spill on a freighter that was unloading a tank of chlorine, and it killed a bunch of people, created this yellow gas and everything. It's very toxic, terrible stuff. So if it does escape, if it mixes with water, forms chlorine gas, and probably going to die. It's also fatal if you inhale it or absorb it through the skin. So very nasty stuff. Have to be very careful in using this stuff. Perchlorofluoride is the next one, ClO3F. This is a stable derivative of perchloric acid. It's a lot less toxic and much less reactive than chlorine trifluoride. It pairs pretty well with carbon-containing fuels. So if you look at the hydrocarbons, which we'll talk about, so something like RP1 or rocket propellant 1, it works really well with those because the oxygen that's in perchlorofluoride, it reacts really well with the carbon that's in the hydrocarbons. And so when you put those together, it reacts preferentially and it burns really well. In fact, so ClF3 or the perchlorofluoride plus monomethylhydrazine, which we'll talk about all the hydrazines in a little bit, but it's a really good hypergolic fuel. It has a really similar ISP to chlorine trifluoride plus hydrazine, which this is a much more toxic combination. So you take this one, put it with MMH, and it makes a pretty good combination that's overall has the same performance and it's a little bit safer than this other combination. The primary tox hazard that goes along with perchlorofluoride is methemoglobinemia. So there's case reports of workers coming into contact with it, and you see an increase in methemoglobin. So manage that. You know, you're going to increase oxygen intake. I lost my train of thought. So for methemoglobin, you can also use methylene blue, which is kind of a cool antidote. So basically, it just takes methemoglobin and it converts it back to hemoglobin again. So it opens that up for oxygen binding. All right. Next up are the nitrogen oxides, and these are the workhorse storable oxidizers. So LOX is the workhorse cryogenic, and the nitrogen oxides are the workhorse storables. These are in use pretty widely still today. Been used in most rocket systems, so everything from Gemini to Apollo to the space shuttle, the reaction control system, the thrusters, SpaceX Draco thrusters, the Russian Proton rocket. They're used in the thrusters and geosynchronous satellites, so like GPS satellites, that, geosynchronous meaning it stays in one place over the Earth. So over here, this picture, this is SpaceX Dragon capsule. These are the Super Draco thrusters. So this is what happens if there's the Falcon 9 launches and there's an issue with safety or something that puts the astronauts at risk. You can use the launch escape system, or the LES, and so basically that detaches the capsule from the top of the rocket and it pushes it away, and the parachute comes out and the astronaut should be able to escape. So that's what this is firing right here. So this is using nitrogen tetroxide, or NTO, as the oxidizer, and so it's creating the flame, so that helps it separate, flies out, and then the astronauts can return safely. It's very, very toxic. Nitrogen tetroxide, or NTO, super toxic. If you're exposed to inhalation of it, it can cause pulmonary edema. Exposure to 25 to 50 parts per million it starts to irritate the eyes and the nose. If you're exposed to 50 to 100 parts per million, then you'll start to see evidence of pulmonary edema. In some cases, can lead to death. You also get methemoglobinemia, so again, we're looking at oxygen and methylene blue as a treatment. And they can also cause hepatotoxicity. So this is, and also reacts with water to produce nitric acid and nitric oxide, which are super toxic also. I don't think you can really see them on here. So these are the, again, Dragon capsule. These are the Super Draco thrusters firing. I think these are, these small ones here, these are just the regular Draco thrusters. These also use NTO. So if you've seen the video of the Dragon coming into the space station to dock, depending on the view that you're seeing, you see little puffs coming out of the side. Those are the Draco thrusters that are firing. So that's using NTO as the oxidizer, so you're thrusting up in space, getting a line so you can connect to the space station. As they're coming in, they can also use it to align for appropriate re-entry vectors and things like that. So this is one of the reasons, if you've seen recovery of the Dragon capsule, so they come down, they splash down in the ocean, recovery boats go out, they pick up the capsule out of the water, put it on the back of the boat, but they don't immediately open the doors and get the astronauts out. One reason for that is that these RCS thrusters, or the reaction control system thrusters, it uses NTO, and so NTO can get out onto the outside of the capsule here, and if you come in contact with it, again, it can be highly toxic. There's fumes that can be coming off of it, so you have to be running oxygen masks, which is another reason why, I don't know if you remember the crew demo mission, so Bob and Doug, when they splashed back down, there are all these boats that encroached in on the recovery area, and it was kind of a big deal. It's a huge safety issue for the boaters, because if they're exposed to this NTO and any fumes that are coming off of it, they could develop pulmonary edema, methemoglobinemia, hepatotoxicity. So anyway, just something to pay attention to. If you ever watch one of those recoveries, you can kind of see what they're doing, and see that the astronauts will actually stay in the capsule for kind of a prescribed period of time until any of those fumes can dissipate and they can verify that it's safe to open the door. And the reason they pay a lot of attention to this is, and I may have already mentioned it in an earlier lecture, but it's worth bringing up again, in the Apollo-Soyuz test program mission. So this is where NASA sent up an old Apollo capsule, and they linked up with a Russian Soyuz, came together, shook hands down the connection there, separated, came back. So as Deke Slayton, Vance Brand, and Tom Stafford were coming back in through the atmosphere, there was an error that was made. So I think it was Stafford was supposed to flip a switch. Anyway, they were accidentally exposed to pretty significant hydrazine and nitrogen tetroxide fumes, or NTO fumes. And this was caused by fuel that was leaking out from unignited reaction control system thrusters. So these propellants were leaking out. Stafford was supposed to turn off the RCS. He said it was too noisy in the capsule when they were re-entering. He missed that call out on the checklist, so the RCS didn't get shut off. So this propellant leaked out, came in through the vents into the capsule. Vance Brand actually lost consciousness for about 40 seconds as they were coming in. Stafford was able to get emergency oxygen, put it on him, and then he gave another one to Slayton, so that revived him. Came back to, they ended up being hospitalized for 2 weeks after they recovered. They had pretty significant chemical pneumonitis, evidence of pulmonary edema. They had methemoglobinemia on top of that. So it was a pretty significant deal. And I mean, this was related to an error. Just because a checklist call out was missed, they didn't get the RCS shut off, started coming in through the vents, and Brand was actually sitting closest to the vent, which makes sense that he was the one that passed out because he had the highest exposure to it. And actually, when they went back and figured it out and ran all the labs and everything, they were exposed to 250 parts per million of nitrogen tetroxide. So if you remember, was it 50 to 100 can cause pulmonary edema and potential death. So exposed to 2.5 times that amount. So they're pretty lucky that they ended up surviving. They were in the hospital for a while and had chemical pneumonitis. But it was a pretty severe issue. Okay, hydrogen peroxide is our next durable oxidizer. This one... peroxide was used in World War II in Germany. Were the ones that developed it. It was called T-Stoff. So again, they had their A-Stoff, T-Stoff, they also had C-Stoff. I don't know where all the stuff came from. Anyway, they used this peroxide, developed it for missiles and for aircraft. And actually this is the ME-163A Comet. It was actually the first rocket-powered jet that was in use. And it used used peroxide as a monopropellant. So monopropellant means it provided, it was just this peroxide that basically used its own chemical decomposition to create a driving force. So basically what would happen here is peroxide, so they had the jet engine or the rocket engine, peroxide entered into a combustion chamber and it got mixed with calcium permanganate in this water solution. So once it hit this water and calcium permanganate, it catalyzed the decomposition of peroxide. So peroxide broke apart, it liberated water and oxygen. That water turned into superheated steam, and so then they used that steam power to drive turbines, which then drove the pumps, which then forced that oxygen that was liberated, plus an alcohol that was coming in, into the main combustion chamber, which then created a propulsive force. So this peroxide was being used initially as a monoprop to drive the turbines, which then fed the fuel into the rocket, which then created the propulsion. Today it can be used as a monopropellant by bringing it in contact with silver. The silver acts as a catalyst and you get the same reaction. So you get water plus oxygen, that water turns into steam, and then the steam can also eject at a very high speed through a rocket nozzle. So it can be used as like a reaction control system thruster as a monopropellant, runs across that catalytic bed, creates the steam, and you get your propellant force. So they start off with the ME-163A, used peroxide as a monoprop. ME-163B used a bipropellant system, so that's where they took peroxide, and then this other liquid called C-Stoff. So C-Stoff was another one of the stoffs, but it was hydrazine-based fuel that had 30% hydrazine. It was like 57% methanol, and then the rest was water. The only reason it wasn't all hydrazine is they didn't have the capability to make it. It was really hard to come by. It was expensive to make, so they used this kind of dilute fuel. Anyway, beside the point. So that was the C-Stoff. So hydrazine plus peroxide, and then that created the propellant force for the ME-163B, so kind of the second version of this. And what they did with that in the war, it wasn't used for dogfighting, or it wasn't a fighter necessarily. It didn't go up and dogfight with P-51s or things like that. But basically when bomber formations were coming over, they'd launch these ME-163s, so they'd light that peroxide, or start that combustion, and then this thing would shoot straight up. It would fly through the middle formation of bombers and just take pot shots at them. So go up, shoot its gun, run out of propellant, come back down, shoot its gun at the bombers on the way back down. And that was it. That was his entire mission profile. It was also pretty susceptible to explosions. Most pilots that flew it didn't make it back. They were also, this was later in the war, and so they're running out of pilots anyway. And so they kind of, unfortunately, became disposable commodities, essentially. Anyway, back to peroxide. Peroxide's not as corrosive as nitric acid, which is great. It doesn't produce toxic fumes, which is also great. We talked about the monopropellant side of it. As far as post-war use goes, it's been used in missiles. It's been used in research aircraft as kind of a supplemental rocket on the side of a research aircraft. It's been used in satellite attitude control systems. It's also still used in the Soyuz, so the Russian Soyuz descent reaction control system thrusters. So when the Soyuz capsule's coming back into the atmosphere, it uses the monopropellant to align it for proper reentry. Originally, so in the 1960s here in the United States, it was developed as a biprop using peroxide plus JP4, which is jet fuel. It was used in the NF-104, so that's the NASA. Actually, I've got it right here. Yeah, so this is an F-104, but so NASA used these as a test bed for this peroxide bipropellant. Peroxide plus JP4 is the bipropellant to use rocket engines that supplemented it. And Chuck Yeager actually flew one of these. If you watch The Right Stuff, the movie, the whole story's in there about it. It's really interesting. So basically, I mean, the story is kind of cool, so I'm going to go through a little bit of this with you. So the NF-104 you can see right here, had this rocket engine that was mounted right above the afterburner nozzle on the F-104. So you used peroxide and JP4, and when you ignited it, it would kick out about 6,000 pounds of thrust, which is a huge kick in the butt. So it was like a super afterburner. The main engine plus the regular afterburner would get you up to about 60,000 feet. At that point, you cut in the rocket, and that takes you from 60,000 feet up to 120 to 140,000 feet. The only problem is that no one had, prior to Yeager getting in this thing, had really rung out the 104 before, like at these altitudes, at these speeds. So they didn't really know how it would handle in that higher atmosphere. So the higher you get in the atmosphere, the fewer molecules there are, the thinner the atmosphere is. How airplanes fly is it relies on those molecules flying over the wings to maintain lift. So you get higher flow above the wing, which means you have higher pressure below the wing, which keeps it pushing up. When you get into the high atmosphere, you don't have as many molecules flowing over, so you lose dynamic control like that. You can't use your typical control surfaces. So basically, no one really knew what the performance envelope was going to look like with this F-104. So the morning that Yeager was supposed to take this up, everything so far was going fine. I'd taken up to 108,000 feet. Cut in the rocket engine, worked just fine. So the rocket, basically once it gets cut in right here, it kicks the jet up at 60, at a 50-degree angle of attack. And, God, I lost my... basically, I'll just kind of cut this short, but so it had these rocket thrusters in the nose too. So basically, once it got up into the high atmosphere, you couldn't nose down. So when you push the control stick forward, it would typically cause these horizontal stabilizers to pitch, or the ailerons and the elevators to pitch, and so it put it back down. But in the high atmosphere, you can't do that because there's no airflow over there, or there's not enough. And so they had rocket thrusters in the nose, which when they'd fire, so it'd fire up, put the nose back down, and then you could come back in and get your descent profile in place. So anyway, Yeager gets up there. He goes to fire the thrusters, but the thrusters don't work. So basically, essentially what happened is he got up at this angle right here. He was still low enough in the atmosphere where there was... he had aerodynamic flow over the surfaces and still used the control surfaces, so he had good control authority there. The problem is, at the angle of attack, it cut off the airflow to the elevators, and so, if you pushed it forward, it wasn't going to do anything, even though he still had airflow over the wings and everything. So we used the rocket thrusters trying to get it to push back down, but there was still enough atmospheric force that kept it from doing that. So the rocket thrusters weren't powerful enough to push that nose back over again. And so we got up there and then lost control authority and then ended up going to a flat spin, spun all the way down to 8,500 feet, ejected, but the rocket motor, like, it got twisted around and it burned half of his, well, it didn't burn half his face off. He had massive, like, second, third degree burns on his face from this. And it was kind of a miracle he survived. Anyway, it's a really interesting story. Recommend reading the book, The Right Stuff, or watching the movie, The Right Stuff. Really, really good. Peroxide's got a good freezing point, or a high freezing point of 11 degrees and slow thermal decomposition. So the freezing point's really not great. It's not well suited for colder environments. Not good for widespread use. This I won't play through here. You guys, I think, should be able to watch the video on your own if you want to. This is basically they found this lost video of that rocket flight, or of that F-104 flight where they used the rocket on the back. So this is the video of Chuck Yeager flying, getting into the spin, and ejecting. It's actually pretty good. 6.5 minutes, so I won't go through it on here. Peroxide, it's a super powerful oxidizer, but it combines explosively with combustible materials. So just like I was talking about with liquid oxygen, don't wear cotton or wool if you're using highly concentrated peroxide. So when you get up into the 98% peroxides, if you're wearing wool or cotton, you may spontaneously combust. So I would avoid that. If you get it on your skin, as long as you wash it off, it's not a big deal. It might cause a little bit of skin blanching. And it can lead to a burn if you keep it on there. So, if you poured 98% peroxide on your hand and just kept it there for a long time, which I don't know why you would, but it can cause a burn after prolonged contact. Otherwise, as long as you wash it off, you'll be just fine. Good news is skin contact doesn't lead to systemic toxicity. So, even if you do leave it sitting there forever, it's not going to cause systemic toxicity. Now, if you, for some reason, are exposed to aerosolized peroxide or its vapors, then it can cause tissue damage in the eyes. It can get into the lungs and into the trachea. All right, next up are the fuming nitric acids, which are still in use in some cases, but they kind of had their heyday back in kind of the golden age of the space era. It was used extensively as an oxidizer in the early space program. It gave rise to the term hypergolic. So the term hypergolic came from this. So basically, scientists discovered that certain fuels, they ignited spontaneously when they came into contact with nitric acid. There was a guy, Wolfgang Noguera. He came up with the code name Ignal for nitric acid. And then the fuels that he'd use with it, he called ergols. And so he was pretty deft at his Latin etymology, and he coined the term hypergolic. So he combined Ignal and ergol and called it hypergol, and became synonymous with spontaneous igniters. Since then, hypergol, all of its derivatives, hypergolic, hyperglicity, all that, it's part of the lexicon in pretty much most languages at this point. So that's where all that came from. Nitric acids have a good liquid range. They're very hypergolic with most amine-based fuels. They are very corrosive, though, and they tend to thermally decompose, so they'll generate a lot of heat. They're very corrosive. Water enhances this decomposition. And actually what they found is when they mixed it with water, it led to what's called white fuming nitric acid, which is a very toxic substance to come in contact with. The fume is very toxic. It's very caustic when you come in to dermal contact with it. From there, what they found is that adding 6% nitric oxide to white fuming nitric acid, or WFNA, yielded something that's called red fuming nitric acid, or RFNA. RFNA tended to be a lot more stable and slightly less toxic. So WFNA saw very limited use. RFNA saw a lot more widespread use. One thing that's kind of interesting is just by chance, when they're putting the nitric acids or they're putting the RFNA and the WFNA in the tanks, it was eating away at the tanks, so it was leading to decomposition over time. They had to replace tanks pretty frequently. And just by random chance, they found that if you coat the tanks in hydrofluoric acid, for some reason it inhibited that decomposition process. And so from there, what they did was they started mixing the RFNA with fluorine, and fluorinating became the standard and became known as IRFNA, or inhibited red fuming nitric acid. So it kind of became the standard. Add fluorine to your RFNA, stabilizes it, keeps it from eating away the containers, and you have a lot better storability with that. RFNA in and of itself, it's a clear liquid, but it has a little bit of a yellow to a reddish tint. Like the name implies, it's very strongly fuming, and it's highly, highly corrosive. The fumes, if you're exposed to them, they're suffocating. They're highly poisonous, so I recommend don't get around RFNA fumes, or WFNA for that matter. It is a very, very powerful oxidizer, so in the lines of fluorine and things like that, it attacks most organic materials very explosively. So it's a great hypergol. It's fantastic from a hypergolic perspective. If you come in contact with it, it'll immediately stain your skin yellow, and it'll stay like that for quite a while until the skin replaces itself. It quickly develops to a burn, so if you found yourself in contact with RFNA, wash it off as quickly as you can. Inhalation, so I mentioned, it's very toxic if it gets inhaled. Obviously, it's going to lead to coughing, it leads to asthmatic breathing, you get nausea and vomiting. Interestingly, it can cause thrombocythemia, so the opposite of thrombocytopenia. It increases platelet count, and it's also been associated with fatal pulmonary edema. On something you don't normally think about with this, chronic exposure leads to tooth decay. So scientists who had worked pretty closely with this found themselves with more tooth decay than what would typically be expected. It also can trigger emphysema, respiratory irritation, and then it can lead to nasal and oral ulceration. So not pleasant stuff. It's a great oxidizer, but yeah, it's pretty nasty stuff. Okay, next, our final section anyway, are on the fuels. So we're going to talk about, we talked about the oxidizers already. Now we're going to talk about the fuels. So first up are the cryogenic fuels. So again, I have Starship on here. Starship uses a combination called methalox. So it uses liquid oxygen, or LOX as its oxidizer. So that's the big tank down here. And it uses liquid methane as its fuel. So it's liquid methane is up here. These are both cryogenics. So they're both have very low boiling points. So they have to be kept very, very cold. And you tend to see these huge clouds that go along with the fueling process. First up is hydrogen. Sometimes you'll see it abbreviated LH2, which stands for liquid hydrogen. So if you ever see LH2, it's liquid hydrogen. Liquid methane's abbreviated LCH3 sometimes, so the L just stands for liquid. Hydrogen's the most abundant molecule in the universe. It's also the lightest element. It takes 600 sextillion atoms of hydrogen to make 1 gram. So pretty light, I'd say. It's got a great heat release, really high heat release, very low molecular weight combustion products, which again is advantageous. You need that increased mass flow, so the lighter the molecules that you're ejecting, the greater mass flow you can get. It's the fuel of choice with either liquid oxygen or with fluorine as an oxidizer. Again, liquid oxygen is by far and away the most commonly used oxidizer in terms of cryogenics. One of the bigger problems that you run into with hydrogen is the fact that it's especially prone to leaks. It's a cryogenic, so it has to be kept really cold, and so when it's really cold and it's under high pressure, it can leak pretty easily. That was a consistent problem for the space shuttle, which the space shuttle used liquid hydrogen with liquid oxygen, and it's so just to kind of back up a little bit. So this is SLS right here. These are the solid fuel boosters on the side, and then the center tank here, this is what burns liquid hydrogen and liquid oxygen. Same setup as the space shuttle. So the space shuttle had the two solid fuel boosters on the side, and then it had the liquid fuel booster in the center, and it burned, again, the bright orange tank that you'd always see, burned liquid oxygen and liquid hydrogen as the fuel. It was a consistent issue that arose with the space shuttle and is already rising with the Space Launch System, or the SLS. So the problem is, hydrogen is tiny, right? So it squeezes through the tiniest gaps that it can find really, really easily. It's not a huge problem at ambient temperature and pressure, but when it's super chilled, so it has to be super chilled to be loaded into the rocket or into the tanks, and it's under high pressure, then it's going to flow everywhere. Because it's cryogenic, it boils off almost immediately. So when you're fueling a rocket like this, the fueling hoses have to stay connected to the rocket up until the second of launch in order to keep those tanks topped off. So that gets connected to the side of the rocket, and it uses what's called a QD, or quick disconnect, to pop those off, and then the rocket can launch. Now the tricky thing is that these quick disconnect fail-safes, that can't be bolted together so tightly to block off the flow of liquid hydrogen. So what that means is it has to have some spacing in it, which makes it really difficult to seal those connections because it's under such high pressure and low temperature. So low temperature plus high pressure equals hydrogen flows everywhere, which makes it really, really hard to seal, which means that liquid hydrogen can start to leak out, and you form these high concentration pockets of hydrogen around the area, which is not a good thing. So overall, they have a tolerance of 4% concentration of liquid hydrogen around an area. Anything more than that becomes a huge fire risk. And the problem is that you don't want to mess around with the hydrogen fire. Now, hydrogen and oxygen, when you put them together, they aren't hypergolic with each other. It takes a little bit of a spark. But they're very, very easily ignited when you put them together. So again, just a very small spark can make them go boom. And it's a murderous explosion. And another issue is that in these higher concentrations of liquid hydrogen, if liquid hydrogen does catch fire, the flame's almost invisible. So a very true statement is that if you have a liquid hydrogen fire in the middle of the day, you could walk right in the middle of the flame and have no idea. You'd feel the burn once you got into it, but you would never see the flame. So these flames are pretty much invisible. So it becomes a very dangerous proposition. So they have the tolerance of 4%. Anything higher than that, then it leads essentially to a scrub. So actually with the space shuttle, they had an average of 1 scrub per mission, which means that whenever the space shuttle was supposed to be launched on the day and time, it essentially never launched on the day and the time it was supposed to. In some missions, they had 5 scrubs before they could ever launch, and most of the time this is because of liquid hydrogen leaks that were going on. So you can't have these leaks, you can't have these high concentrations. If you guys watched the first attempt to launch the SLS back in September, they had it out on the launch pad. They started the fueling process, and then they had to scrub. What happened was they started seeing concentrations of 8 to 12% of liquid hydrogen around this gasket where they're trying to fuel it. And so the thought was, okay, let's pause the fueling for a minute. Let's let this valve and the gaskets around it kind of thaw out a little bit, and then we can try to start again. See if that seals itself, and then it can start fueling again. They did. It didn't seal. They kept leaking, so they had to scrub it and move the rocket back to the vehicle assembly building. So again, it's a very significant issue with liquid hydrogen. It's a pain in the butt to work with for that reason, because it's so light, it just flows everywhere. So massive fire risk when it goes when you're using it. So you have to be very, very careful with it. Now that being said, it's non-toxic, so we're not worried about triggering pulmonary edema, hemoglobinemia, corrosive burns, and things like that. The biggest hazard that's associated with it is that it's cryogenic, which means that if you come in contact with it, then you can get frostbite. So you just have to be careful when you're using it. One thing they've found that they've used to some degree is it's called slush hydrogen. So it's basically a mix of liquid hydrogen and frozen hydrogen. So you put those two together, it's cool because it increases the density and it improves the storability of it, so you're not just boiling everything off right away, which makes it more of an attractive option for space vehicles. So, if you're going to use it in space, you probably use the slush hydrogen. Kind of like on the Apollo missions, they used slush oxygen, which is actually what, a problem with, on Apollo 13, they had their slush hydrogen tank. They went to initiate a stir, which basically just kind of mixed it up, and it kept it from like freezing solid in one place and being gaseous in the other, so it just kept it in slush. And then the warmer that was in there to do that sparked, and that's what caused the explosion. So anyway, kind of a sidebar, probably a reiteration of things I've already said. All right, next up are the cryogenic hydrocarbons. So this is methane, ethane, ethene, and propane. Of these, methane is the one that's going to get the most publicity. So this is actually what SpaceX is using, again, in the Starship. So I love this picture of the full stack Starship. So down here you have the booster. Up here you have the second stage, which is what will be used to, so this is the orbital vehicle. So if it carries astronauts or it's just carrying cargo, this is what's going to go up. Anyway, they're using methane. So methane has better performance and better combustion characteristics than RP1, which is rocket propellant, which is kerosene. The primary disadvantage is that it's cryogenic, so it's harder to work with, especially on Earth. But the reason that SpaceX is using it, that's cool rationale. NASA was actually going to do this they started looking at this back in the 60s when they were looking at creating a vehicle to go to Mars. Before we went to the moon, we were already looking at plans to go to Mars, which really kind of makes me mad that everything I don't know what happened, but things got screwed up. Missions got abandoned. We should have been to Mars well before now. Anyway, sidebar, we'll get off onto that. SpaceX, they're going to go to Mars. Elon Musk has it in his mind, we're going to Mars, it's going to happen. And so the decision was made, okay, let's look at all these available fuels and oxidizers. Methane's got a pretty good profile, it's got pretty good performance, it's got pretty good combustion characteristics, but it's cryogenic, so it's a pain in the butt to work with. By nature, because it's cryogenic, it's not as dense as other fuels are going to be, other non-cryogens are going to be, so it's harder to get the tank full, to really get it packed in. So why would we consider using methane to go to Mars? Well, the reason is that once you get to Mars, let's say that you're using kerosene, you're using RP1 to get there. So you use up your fuel load, you've gone through Tsiolkovsky's rocket equation, figured out your the propellant mass that you need to get your delta V to escape velocity to get to Mars, and then you land, and now you're out of fuel. How are you going to get back? Well, ideally we'd make more fuel, but if you're talking about hydrocarbons like RP1, how are you going to make that on Mars? It's going to be really difficult. But if you look at methane, you can make methane on Mars actually pretty easily. What you do, you send the Starship to Mars, you got your lander down, you come down the land, you immediately set up a solar structure, and you start to generate solar electricity on the surface of Mars. With this, you can send carbon dioxide through electrolysis, which then, when you mix that with the water from the ice that's on Mars, then you generate methane. And all of a sudden, you're making your own fuel, and now you've made enough propellant to come back to Earth. So really, it just makes the most sense to use a fuel that you can actually make on the surface of Mars. The other fuels that you look at, you really can't do that. So that's kind of the whole decision-making process behind using methane here. Methane, it's non-toxic, although if you're exposed to high enough concentrations, it's a simple asphyxiant. It's really not that surprising. If you walk in the middle of a bunch of smoke or anything like that, you have a hard time catching your breath. It starts to displace oxygen from hemoglobin, so a simple asphyxiant. Otherwise, it's non-toxic, which is fantastic too. All right. The final segment will be over storable fuels. So there's only a few cryogenics, so liquid hydrogen, methane are kind of the two big ones. So now let's look at the storables. So of the storables, RP1 or kerosene, it's a kerosene derivative. It's the most widely used rocket fuel. Typically it's used with a liquid oxygen oxidizer. So Atlas missiles, Thor, Titan 1, Saturn V. So this is the Apollo 11 mission. Used RP1 mixed with liquid oxygen, ignites, and this is what you see right here. And actually kind of a cool thing, if you see a rocket with a bright plume like this coming out, it tells you pretty much right away that it's RP1 plus liquid oxygen. So basically you get unreacted carbon that gets into the exhaust stream, it reacts, and you get this really bright glow that comes out of it. Rockets that launch that have, I'm not going to call it an invisible flame, but a much lighter flame that you can actually see the shock diamonds that are forming in it. That's using non-hydrocarbon, non-carbon containing fuels. So if you have watched, or if you go back and watch on SpaceX, watch any of the Starship test launches, SN8, all the early launches. When you watch the flame coming out from underneath there, it's burning methane plus oxygen. It doesn't have this huge bright glow that you see right here. It's much more of a purplish kind of color, and you can see, so the shock diamonds, when you see the flame come down like this and then it comes back out like that, or shock diamonds, mock diamonds, things like that. So anyway, kind of a sidebar, but kind of an interesting thing. And then also Falcon 9, the first stage of Falcon 9 uses RP1 plus liquid oxygen. So for that, it's got good density. We're just, Falcon 9s are used for low Earth orbit missions, not going to Mars to make its own fuel or anything like that. So RP1 is a good choice for Falcon 9. Basically, it's JP4 with controlled aromatic content. Helps eliminate coking formation. So coke formation is that, carbonaceous gunk that can fill, can clog passages and things like that, and it can make it a lot less efficient. It also screws with regenerative cooling. So if you watch the How Do Rocket Engines Work video, I know that in order to keep the motor from burning itself up, it runs fuel. A lot of them run fuel through the exhaust nozzles, and that helps to cool it, so it's regenerative cooling. If you start getting coke deposition in there, then it inhibits the ability to cool the engine, starts clogging everything up, and then you can go boom. So some hydrocarbons decompose under high temperatures. So if the temperature is too high, then decomposition of carbon, again, can lead to coking and leads to clogged passages. And can decrease heat transfer rate, so it just jacks with cooling. Robert Goddard, so I already mentioned him just a second ago. Sorry, my dog just snuck in here. Robert Goddard used liquid oxygen. He also used automotive grade fuel. So he just go out to your gas station, pump some gas, mix that with liquid oxygen, burn it, and that's what he used for rocketry, basically. The Air Force used, for a period of time, used JP4 plus red fuming nitric acid, and they created, I mentioned, these JATO rockets. So this is a B-57 bomber. It was used in the 60s, kind of in between World War II and Vietnam. But it was this big, lumbering jet that was really hard to get off the ground, and they were looking for improved performance. And so they strapped all these rockets to the bottom of it. And these are called JATO, or JATOs, Jet Assisted Takeoff. And so basically they took the JP4, red fuming nitric acid, mixed that together. Remember, RFNA, it's very hypergolic. Hits the JP4 and in theory, anyway. The problem they ran into was that initially JP4, there weren't a lot of quality controls around the production of it. So batches were different. They had different composition, contaminants, things like that. And so overall, the combination was kind of unreliable. There was a lot of combustion instability. There were hard starts, that's when we were talking about reliability of hypergolics, where if it floods into the combustion chamber and it doesn't immediately ignite. Then more comes in, then it goes boom. Now that's a hard start. So you want to avoid hard starts because they'll destroy your engine really, really quickly. The problem I had with this, again, this probably all revolved around the impurities and the quality control around JP4. But there were a lot of hard starts, and so it wasn't a super reliable system. And so it didn't see a lot of use outside of the Air Force for these limited applications for JATO, the Jet Assisted Takeoff. Toxicity of hydrocarbons, we kind of talked a little bit about it. It's generally harmless to the skin as long as it gets rinsed off pretty quickly. Although, if you stick your hand into a tank of RP1, you can have necrosis. So just don't stick your hand into a tank of rocket fuel, and I think you'll be okay. It does have drying solvent type of an effect. Very little danger of systemic absorption, unless you have cuts and mucous membranes and you dunk all that in there, then you can have systemic absorption. But in general, it's nothing to worry about. Vapor inhalation is kind of the biggest risk that goes along with it, though. It can cause headache, nausea, vomiting, convulsions. In severe cases, you can become cyanotic, become comatose. All right, then hydrazine. So the rest of this lecture is going to be on hydrazine because it's the most widely used. It's also really dangerous. It's pretty nasty stuff, but it works really well too. So it's kind of a trade-off there. Hydrazine, it's an inorganic, colorless, highly toxic reducing agent. Its liquid properties are pretty comparable to water. It's a little bit more viscous than water is, but in general it kind of looks like water. It was developed by the Germans, so I mentioned the Seestoff, which was a mix of hydrazine, methanol, and water. Again, the methanol and water were only in there because they couldn't make pure hydrazine. Today, it's used extensively as a propellant. It's a great hypergolic fuel, and it's also used as a monopropellant in some cases. We produce over 45,000 tons of the stuff annually. This is actually the ME163B that I mentioned earlier that used that combination of C-Stoff, the hydrazine, plus T-Stoff and peroxide. And so that was the jet-powered, or rocket-powered jet. Cool concept. Glad it didn't come into widespread use because that could have been a game changer in the war. So I'm glad all the German stuff came in too late to make an impact. But there was a lot of cool technology that came out of it for sure. Hydrazine is super toxic. Toxic. It's a hazard to human health, and it's a hazard to environmental safety. NASA's actually made moves to try to find a less toxic substitute for hydrazine, but haven't found much success as of yet. There are two primary derivatives of hydrazine that are in wide use today, monomethyl hydrazine, or MMH, and then unsymmetrical dimethylhydrazine, or UDMH, which I'll probably just say MMH and UDMH because it's a lot easier than saying the other. Again, the hydrazines they're very potent reducing agents, and so just a small amount of damage, or a small amount, can lead to significant soft tissue damage, cause pulmonary injury, can trigger seizures, make patients comatose, and can lead to death. The good news with all this is that there are extensive safety protocols surrounding its use. So there are very, very few reports of human toxicity that are involved. There are a few, but for the most part, safety procedures are in place that dramatically minimize the risk of human exposure to this. It's used in the F-16, so it's used in the F-16's emergency power unit. So F-16, single engine jet, so if your engine goes out, you're in a little bit of trouble. It's also the first fly-by-wire jet, which means that it doesn't use cables and actuators and all that, or to actuate the control surfaces. It's all electronic input. So if you lose your engine, lose your electrical, really your only option would theoretically be to eject, which means that you're going to waste this awesome jet. Potentially it's going to crash into a crowded population. We don't want to have that happen. And so they built an EPU into this, an emergency power unit. And what it does is it has this fuel tank that's filled with hydrazine. It's filled with hydrazine, so it's called H70. So it's 70% hydrazine, 30% water. But you have this hydrazine tank. It flows it over a catalytic bed, which then triggers a spontaneous decomposition, which then provides propulsive force. So it uses that force to drive generators in the aircraft, and then it restores power so the pilot can have enough control authority to make an emergency landing. So it's something you kind of need in a single engine jet like that. But anyway, so hydrazine is, there are a lot of safety protocols around flying or being around an F-16 because of the presence of hydrazine. So this is, in all routine daily use, this is probably where the majority of exposure potential is going to come from, is the F-16. It's also in use in the SpaceX, the Draco and the Super Draco thrusters. So I had already showed you the picture of the Super Dracos firing. Show you this one. So here, so you can see the flame. You can see those shock diamonds forming in there. Versus if it was RP1, you'd have like the really bright flame, so it's burning that carbon that comes into it. But anyway, that was a Super Draco thruster. So this is just a little diagram of the Dragon capsule. So you have your Super Dracos here. So this is for the launch escape system. So if there's a problem on top of the rocket, either right before launch or immediately after launch, those can fire, causes separation, and then the parachute can pop and the astronauts will survive. And then also in space and on re-entry, they have the Draco thrusters. So you're using NTO plus hydrazine, and that provides the force and your control authority. All right, hydrazine, it fumes. It creates fumes in the air and gives off an ammonia-like odor. The problem is that you can't rely on smell alone to let you know if you've been exposed to hydrazine fumes. The issue is that the body can't physically detect the odor until you've already been exposed to 20 times the permissible amount. So basically by the time that you smell it, you have to go to the doctor. You have to, or go to the hospital. You're going to be at risk for pulmonary injury, seizures, things like that. So if you can smell it, it's too late. Unfortunately, it's not a good indicator of exposure. It's very hygroscopic. Hygroscopic means that it pulls water out of the air. It also removes carbon dioxide from the air, so this kind of complicates the handling of it. Close contact during maintenance, so crew chiefs, maintenance crew working on the F-16, they can, or even work, SpaceX engineers working on the Draco thrusters. They can routinely come into contact with, or routine maintenance can lead to exposures of about 5 to 8 parts per million. The 2 hour time weighted average is 0.03 parts per million, so you have to be a little bit careful. There have to be really strict safety protocols in place when you're dealing with this stuff. Otherwise, you can pretty quickly exceed that 2 hour TWA. If you're exposed to 50 parts per million for 30 minutes or more, that's considered at high risk for immediate threat of harm. So 50 parts per million is very significant. For monomethyl hydrazine or MMH, it's the exposure limit's 0.04 parts per million over 2 hours, or a 20 part per million time weighted average. UDMH is 0.06/15. And then the 7-day SMAC, so spacecraft maximum allowable concentration for hydrazine, and MMH is 0.04 parts per million. So as an astronaut, you can't be exposed. All these protocols have to be in place so you're not exposed to more than 0.04 parts per million over the course of a week. It's super, super toxic. It denatures proteins. It saponifies adipose tissue. So saponification is basically where you turn fat into soap. So it's kind of like Fight Club. So saponification, you're turning your fat into soap, which is not a really pleasant experience. And it's a very potent base, so it causes alkali caustic burns pretty quickly. Dermatitis, very, very little contact. Caustic injury, so again, it's a very strong base. Can cause burns pretty quickly within 2 minutes. This burned appearance then progresses pretty quickly to papules and edema formation, and then the edema starts to subside over a short period of time. The skin starts to darken, and then you get a predominant chemical burn. So really nasty stuff to touch. If your eyes are exposed to any vapor, you're going to experience conjunctivitis, ocular pain. You're going to have miosis, so pinpoint pupils followed by mydriasis and big pupils. So it's like getting your eyes dilated. You're going to be very light sensitive too. It can lead to corneal injury, which obviously makes sense. You got this super caustic stuff that gets onto your cornea. It can start to degrade that, and it can lead to temporary blindness. If you inhale it, it leads to pulmonary edema, pulmonary effusion, localized bronchial mucosal damage. It can trigger respiratory arrest, and this is typically due to the neurotoxicity that goes along with hydrazine. So it can lead to convulsive effects. It can lead to neurologic dysfunction, which then can lead to respiratory arrest. Vapor exposure, you can get dyspnea, sore throat, burning sensation in the nose and face. Start to get a lot of chest tightness. And when you look at all the derivatives, hydrazine is the nasty one. It's the nastiest one, followed by MMH, and then followed by UDMH. Neurotoxicity can range from either from CNS depression to seizures. So you can have neurodepression up to neuroexcitation, which would be the seizures. The specific toxicity that you see is related to how much and what type of hydrazine you're exposed to. So it's going to be a different picture based on if you're using, if you're exposed to pure hydrazine, to H70, aerosine. So aerosine is kind of a, I can't think of the word that I'm looking for, proprietary mix. I can't remember what company makes it, but there's like aerosine 70, there's aerosine 50. So like aerosine 50, it's a 50-50 mix of UDMH and hydrazine. Aerosine 70, I think, is 70% UDMH, 30% regular hydrazine. So the different type of variant that you're exposed to can lead to different types of symptoms. Hydrazine, so if you're exposed to pure hydrazine, it's a very strong convulsant at high doses, but at lower doses, it's more of a CNS depressant. If you're exposed to MMH or UDMH, it's primarily hyperexcitatory, so you're going to be much more prone to seizures. And you can have tonic-clonic convulsions, and that can actually trigger respiratory arrest, which can lead to death. There have been a few, basically just a handful of case reports of exposures to hydrazine and derivatives. So there were 2 exposures to aerosine 50, so again, it's UDMH plus hydrazine, which they saw twitching, hyperreflexia, clonic movements, so not unlike the serotonin syndrome we talked about pretty recently. One individual that was involved in a UDMH explosion developed agitation and convulsions, which luckily didn't die being in a UDMH explosion, a hypergolic explosion. And then there haven't been any human reports of MMH exposure yet. As far as animal studies go with hydrazine, what they've noticed that there's a dramatic, so just pure hydrazine, there's a dramatic GABA upregulation. So GABA, inhibitory neurotransmitter, so it leads to CNS depression. And then they also see an interference with the urea cycle, which then leads to hyperammonemia. So if your urea cycle is not working, you're not processing ammonia, hyperammonemia leads to altered mental status also. As far as UDMH and MMH go, what they found is kind of interesting. It interferes with pyridoxal 5-phosphate or PLP. It reduces glutamic acid decarboxylase, and then all this leads to a reduced production of GABA. So if you remember back a couple slides ago, with hydrazine, you can get CNS depression, and then with UDMH and MMH, that's neuroexcitation. And so with this interruption with PLP and GAD, it leads to decreased GABA, which then leads to an overall neuroexcitatory picture. What they found too is that pyridoxine or vitamin B6 can actually have a protective effect. So if someone's exposed to UDMH or MMH, then it's a good idea to give them vitamin B6, which can help mitigate some of those effects. Hepatotoxicity has been reported in both acute and chronic exposures. They've seen LFTs increase within about 5 hours of exposure. Those will continue increasing for a period of about a week, and then it takes about a month for all that to resolve. So a fair amount of hepatotoxicity that goes with it. There has been a human case report after someone who was exposed to hydrazine and had chronic inhalation of it. They died, unfortunately, from it, and what they found on autopsy was that they had focal hepatic necrosis and cell degeneration, so pretty nasty on the liver. Chronic exposure to UDMH, it's been associated with ALT elevation and the formation of fatty liver, so steatohepatitis. And then in animals, they found that it interferes with pyridoxine-dependent enzymes in the liver, kind of hence the vitamin B6 recommendation. And then hydrazine is a powerful reducing agent. So this reducing agent, it leads to glutathione depletion. So it's a lot like what alcohol does in the liver. It leads to glutathione depletion, which means that it's going to make sense that we can potentially give N-acetylcysteine in this case to manage that glutathione depletion and preserve liver function. It causes some blood dyscrasias, hematotoxicity. All of them can cause hemolytic anemia. All of them, hydrazine and MMH can cause methemoglobinemia. So a lot of these fuels and oxidizers can cause methemoglobinemia. So that's something we definitely have to be aware of. And it can lead to hemoglobin denaturation. Of these, MMH, or between the derivatives, MMH is the most toxic with regard to hematologic disturbances. Exposure to 90 parts per million of MMH can lead to clinically significant methemoglobinemia within about 10 minutes. So it doesn't take very long, and you're going to start to get cyanotic. So what do you do for exposed? So this is actually a picture of an Italian F-16 that there was a potential hydrazine leak. And so you have the pilot, you have the WISO, or the weapons system officer. They have to keep their hands on their head, saying they're off the control surfaces. And then you have the maintenance personnel, so they're in their full protective gear. So they have to be in full PPE to avoid any type of exposure to it, looking to see if there's actually a leak under there. The recommendations for hydrazine toxicity treatment, these all come from animal studies, observational data, and expert opinion. So it's basically, this is what we know can happen with hydrazine exposure. Haven't had enough cases to work out an evidence-based treatment algorithm. So we're going to use what we think we should in this case, and what makes sense. The first thing and the most obvious thing is decontamination. If someone's exposed to hydrazine, if they get hydrazine on them, they have to be fully decontaminated. So, for example, if this guy, if they did have a hydrazine leak in this F-16, then, and he wasn't wearing full PPE, got exposed to it, then this would trigger an emergency, and you have to be fully decontaminated, which we'll talk about in the next slide. Go through supportive measures and treatment neurologic sequelae. So the first thing is, so this guy gets exposed to hydrazine. First, need to move him at least 75 feet away from the site. So you want to get away from all the fumes, anything that can worsen the picture. And then decontamination. This is the critical action. You have to remove all clothing. So all clothes are going to be cut off. And I guess it probably makes sense to say that rescue personnel, so if someone's exposed to hydrazine, the rescue personnel have to be wearing this PPE because they can't, you can't go help someone but then be exposed yourself, and now you have two patients that are in need of help. So anyway, common sense statement. Remove all the clothing. Hydrazine, MMH, UDMH, they're all water soluble. And so if you get it on your skin, it can be pretty easily removed with water. So we need copious irrigation for at least 15 minutes over all surfaces, exposed or not. Make sure it's all off. Clothes have to be off, because if any got on the clothes and maintain contact, you're going to have, necrosis. You're going to have burns, alkali burns and things like that. You don't want that fat saponification to happen either. And then you can't transfer the patient to the hospital before they've been fully decontaminated. Again, it's source control. You don't want to contaminate others in the ambulance, others in the hospital, so get them washed off first, decontaminate them, and then transport them to the hospital. At the same time this is going on, you need to figure out what led to the exposure. What derivatives was the patient exposed to? Was it Aerosine 50, Aerosine 70, MMH, UDMH, straight up hydrazine, neat? So neat just means it's undiluted. So if the F-16's EPU fires, it can trigger release of 24 grams of unreacted hydrazine vapors. And that can get into the exhaust. 99% of that will still make it through the catalytic bed, and it'll convert to ammonia and water. And so if you're exposed to this high concentration of ammonia, then your treatment protocol is going to be a little bit different too. So you just have to kind of know what you've been exposed to. With hydrazine, you get more CNS depression. With MMH, UDMH, there's GABA depletion, so you get more CNS excitation. So you're going to have different symptomology based on the type that you're exposed to. Inhalation injuries, you're going to manage supportively. So we're going to put them on oxygen. Again, there's the risk of methemoglobinemia, so oxygen is going to help there. If they show any signs of respiratory depression or arrest, we're going to intubate them right away. Get a chest x-ray, because we need to look for pulmonary edema, because that's a very common occurrence with hydrazine exposure. For any neurologic sequela, we mentioned pyridoxine, so we'll give 25 mg per kg of pyridoxine. And just like with someone that presents with an isoniazid overdose, it's the exact same treatment. If they continue seizing after that first 25 mg per kg, you can give another bolus of pyridoxine. Also, benzos, kind of the mantra is when in doubt, benzo out. So if someone comes in seizing, we're going to give them benzo. But if we know they've been exposed to hydrazine, then we'll throw in the pyridoxine. And then N-acetylcysteine also. Makes sense, reduction, redox potential, glutathione depletion. Let's give N-acetylcysteine, which is going to be a glutathione surrogate, which is going to help prevent or mitigate any hepatotoxicity that goes along with it. Okay, and final slide. So this is just kind of the common stuff that's in use today. So most early U.S. rockets, you saw Aerosine 50, so again the 50-50 combo of hydrazine and UDMH as the fuel with nitrogen tetroxide as your oxidizer. The Apollo CSM, Space Shuttle, the reaction control system, SpaceX, Draco, Super Draco thrusters, uses MMH and NTO. Saturn V, Falcon 9 first stages used RP1 and LOX. Space Shuttle, SLS currently, this guy right here, uses LH2 and LOX. Again, we're going to see a lot of problems with that just from fueling alone. It's a pain in the butt. And then the Russians, Roscosmos, they use UDMH and NTO for their Proton rocket. Anyway, hope enjoyed a little bit about rocket propellants. Again, if that is something you're interested in, I definitely recommend Ignition by John Clark. Pretty interesting book. All right, thanks guys, and I'll see you with the next one.